Well, here's the question I asked, and all you have to do to answer it is stick your thumb of your right hand in the direction of the current, which is out of the screen, and curl your fingers, and you'll find that they're curling in the opposite sense to the direction you go around this Amperian path. From your perspective, your fingers should right now be coiling counterclockwise, but the path is showing a clockwise direction, and so that tells you that the enclosed current is negative in our sign convention. Students often get confused about the terminology, the difference between loops, coils, and solenoids. So a loop is simple. It's just a single circular loop of wire with a current in it. A coil is multiple loops on top of each other, and by on top of each other, I mean that they're really all sort of in exactly the same place. All of the loops have the same radius, and they're not displaced from each other. Well, of course, that's totally impossible. They can't all be in the same place. But something like this, where the loops are very nearly the same size and are really very nearly in the same place, is approximately a coil. And here's another thing that could be thought of as approximately a coil. On the other hand, in a solenoid, you have multiple loops, but the length of the bundle of loops is much greater than the radius of the loops, and so something like this is what we would call a solenoid. But often you see things that are neither coils nor solenoids, so in the lab you'll use things that look a lot like this. Well, if you look at them, the loops in them aren't all the same radius, and they're also not all lying approximately in the same plane, but on the other hand, it isn't much longer than its radius, and so it's not a solenoid either. So now let's get the B field inside a solenoid. And I mean deep inside a solenoid, so we need to be far from either end, or alternatively it is a sufficiently long solenoid that we can ignore the fact that it has any ends. And to make it clear which way the current is going, I'm going to draw a cross section through the solenoid. So there are some wires up here. These are the sliced off ends of the wires, and there are the wires down here, which are other sliced off ends of the wires as we took our cross section through the solenoid. And I'm going to say that the current is coming out in these ones up here. Let's now think of the B field at some point inside the solenoid. We must have a B field, say, due to this one, and the right-hand rule will tell you that that B field is this way. And similarly, the right-hand rule will tell you that the B field due to this one down here is also that way. And if you think of one farther along over here, that is going to produce a B field this way, but there's a matching one down here which produces a B field this way, and so again those two will add to one straight in this direction. All of the B fields definitely add up to something which in this picture is straight to the right. What's more, if we are saying this is an infinitely long solenoid, then this whole system has translational symmetry right to left. And so that says that the B field has to be the same everywhere we look along. So I have drawn a B field pointing to the right everywhere inside the solenoid. I've sort of suggested that it must be uniform across the solenoid as well, although I haven't given any argument for that. That's going to turn out to be correct for an infinitely long solenoid, but we won't see it until we're done. So now we need an Amperian path. Well, so we have straight lines for the field lines, and so I'm going to choose a rectangular path. And I am going to take the path out a very long way outside the solenoid. And the reason I'm doing that is that anywhere out here, we will have fields this way due to the nearer currents, and fields this way due to the farther currents. However, if we're far enough out, then the difference in those distances is so small compared to how far we are out here that those should be essentially the same, and we can argue that way out here the B field ought to be 0. So now we're ready to proceed. I'm going to label the segments of my path 1, 2, 3, 4. And I've just argued that the B field out here along path 3 is 0. By the same translational symmetry that I argued in here, everywhere else out here, if there is a B field, it must also be either straight right or straight left. It's going to turn out not to matter, although we're going to be able to show it's actually 0. So that tells us that our B field is perpendicular to paths 2 and 4 everywhere. And I'm going to choose to go around my path this way. If you check that with the enclosed current, that means that the enclosed current is positive with this choice of direction. So now I have and I've argued that this path integral is only the integral along segment 1. And so I can just say it's b dot dl along 1. But I know the B field is parallel to dl everywhere there, and it's constant. So I'm now going to define some distances. I'm going to say that this length here is L, the current is I, and I'm going to say that I have enclosed N bits of wire here. And so that means my total encircled current is just I times N wires, and so it's Ni. So this integral dl is nothing other than L, the length of this segment, and so I just have BL equals mu naught Ni, and so my B field is just mu naught Ni over L. And very commonly we define the coil density, the number of coils in the solenoid per unit length, N over L, and we call it little n. So the B field strength inside the solenoid is just... So this B field strength we've found is the B field along our line 1. And I just want to close off with some further comments about the choice of this Amperian path and what the choice tells us. So notice that if I move the line 1, and let me just move it arbitrarily down here, but it's still inside the solenoid. Well, I haven't changed the encircled current. And so that means the whole argument will play out the same, and I'll come up with the same B field. And no matter where I put the line 1 inside the solenoid, I'm going to come up with the same answer because it doesn't change the encircled current. And so what this is telling us is that not only is the field the same no matter where we look along the length of the solenoid, but it's also uniform no matter how far you look away from the center of the solenoid, as long as you're inside the solenoid. The other thing to realize is that I argued that the B field out here where line 3 is 0, because if I'm far enough away, then the field due to the nearer currents and the field due to the farther currents should cancel. However, notice that now, again, by the same sort of argument, if I just shift this line 3 in closer to the solenoid, but still outside it, once again, I haven't changed the encircled current, and so again, the whole argument plays out the same way. I still know that the line integral along this line is what is giving me the whole value of this line integral, and so the line integral along this new line 3 must be 0 as well. And so the B field is 0 here. And so what we've now seen is that for an infinitely long solenoid, the B field is totally uniform inside the solenoid, and it's exactly 0 everywhere outside the solenoid. Now, of course, that's only an approximation. For a real solenoid, though, if it's long enough, then far away from the ends, the field is very approximately uniform inside, and the field inside is much, much stronger than the field outside.